Hi, in this short lecture, I will talk about the basic data structures in Python. At the end of the lecture, you should know what are the abstract data type stack, queue, stack, and list, how to implement them, and their performance, and be able to recognize their property and where these data type can be used in different type of problem. And also, we want to talk about linked list. So using linked list to implement these type of data and compare the performance of the linked list implement with the Python list implementation. Stacks, queues, and decks and lists are example of what we call data collection, whose items are ordered depending on how they are added or removed. Once an item is added, it stays in that position relative to the other element that came before or came after it. Collections such as these are referred to linear data structure, and usually they have two ends. We call it the top or bottom, left or right, depending on which way you're looking at it. And how data are added and removed from this end determine the type of data structure to use. The first one is a stack. Stack is an order collection items where the addition new items and the removal of the existing items always takes place at the same end. And the most recently added item is the one that is in a position to be removed first. So we call this last in, first out, or LIFO. The last item you put in is the first item you put out. And you can think of the stack like a stack of plate. You add plate to the top and you remove plate from the top. And to implement the stack, and it typically, using object-oriented way, you typically have a constructor to create a new stack, which is empty, and then you will add thing to it. And to add item to the stack, we have push, very similar to the list dot push to push item to the list. We have pop to remove item from the top of the stack. Peek to return the top item from the stack without removing it. It is empty. Check whether the stack is empty. And size, which return the number of items on the stack. And here's one implementation of stack using Python list. In this implementation, the constructor create the stack using empty list. The items is the stack item, and when the constructor is called, it creates an empty list. And I can check whether the list is empty by checking whether the self.items is same as empty list. And I can append or push the item to the stack. Because the stack is implement using list, I will call the list append method to push an item to the end of the list. And using the list pop method, I can pop and return the last item in the list. And to pick, I can return the last item. In this one here, you could actually just call like a self.item items sub -1, which will return the last item in the list. That also be equivalent. Size, using the length function to return how many items in how many items in the items stack. And to try this, we can test the code. Again, we create the empty stack, check whether the stack is empty, and push some item to the list, and check out other stuff. So let's try that in the PyCharm. here is a stack implementation, and here is a code. So I would put a break here and run debugger on it so you can see line by line execution. Let me go to the console. I create a stack. As you can see, it will create an empty list, a empty list. And if the stack is empty, I call isEmpty method. And the isEmpty method check whether the self.items is equal to empty list. And in this case, it is. So you see that the stack is empty. I push 4. I push the word dog. Now the items list now have 2 items in there. So if I want to do a peek, in this case, peek return the last item. What is the last item I just push in? The last item I push in is dog. So as you can see, it return dog. I push true. So I append the item to the at the end of the list. And then I pop. What does the pop do? Pop call pop call the the pop method, which we return and we move the last item, which means the last item that were added to the stack. In this case, the pop return true. And the stack, the size of the stack is 2 now, and as you can see, it's now empty because the size of the stack is there's something in there. I call pop twice. I push 8.4 and then I call pop. I call another pop. So what is the size of the stack right now? Well, the size of the stack is, in this case, 1. And what's in there? In this case, it is the very first item we push in, which is 4. Take a look how the stack implementation work, and how the code work. The main thing is, for the stack, we add stuff to the top of the stack by calling push method, and we move, obtain and remove the last item we push in with the pop method. And in this example, I use a list to implement the stack. The top of the stack is the last element of the list, and the bottom of the stack is the first element of the list. You can implement it differently, being the top element being the first element and the bottom being the last element. And this is the way to do that. I only changed the push method and the pop method implementation. The method itself, the name and the number of parameters stay the same, but how I implement it is different. In this case, I insert the element to the beginning and I pop the first element. When I do peek, I also return just the first element. Instead of return the last element, I return the first element. The length, the isEmpty method, and the constructor do not change. And looking at this stack implementation will do the same thing. And the ability to change the physical implementation of the abstract data type while maintaining the logical characteristic is like an abstraction at work. We have 2 implementations. Both of them work the same. They are both equivalent, but their performance may be different, but how they work is the same. And I mentioned the performance is different, so which one would be better? Which one would be better? If you look at the original implementation, what is the big O running time for push and pop in this implementation? Because this is a list and we append the item to the end of the list, in this case, this would be O1, and we pop the item from the end of the list. This is also O1. It's a constant time. But how about this one? Well, because we're pushing it to the beginning of the list, we have to make room for all the existing items. They all had to move over by one to make room for add a new item. Same thing with the pop. After I pop the first item, everybody to move over. So in this case, the big O running time for the second implementation for push and pop would be linear, depending on how many items in the list that are in the stack. So clearly, even though the implementation are logically equivalent, they have very, very different timing when running performance benchmark testing. And that is the reason we study the runtime efficiency of the algorithm to see which one will be better, given they both work the same. They both give you the same result. So let's try this. Given the following sequence of stack operation, what is the top items on the stack when the sequence is complete? When you do the stack problem, because every time you add something to the stack, you put stuff on top. So imagine this. If I say push X, I create an empty stack. I push X. You can write X on the bottom. And then I push Y. So now Y is on the top. Pop. So I get rid of Y. And then I push Z. So Z will be on the top. And peak. So what is the top item on the stack when the sequence is complete? In this case, it is Z. Given the following sequence of stack operation, what is the top item on the stack when the sequence is complete? Again, I push X, I push Y, I push Z, and then I have a loop there while not m dot is empty, m dot pop. So what happened after the loop finished? What's in the stack? Think about it, and we will talk about this during class.